EE5508 Semiconductor Fundamentals, Part 2, Lecture 2, Optical Processes in Semiconductors. The fundamental energy gaps, or sometimes we call that the band gap of most semiconductors, such as 3-5 materials, the band gap ranges from 0.17 eV, for example, in indium antimonide, to 6.2 eV in aluminum nitride. Photon of sufficient energy can excite electron from the field valence band to the anti-conduction band. As a result, the optical spectra of semiconductor provide a rich source of information on their electronic properties. And in most semiconductors, the photons can also interact with the lattice vibration. So you have to basically assume that the atoms always vibrating at the equilibrium position. So we call this the lattice vibration. Or the photon can also interact with electron localized on defects. So you can study the defects in semiconductors through these photon-electron interactions. So making optical techniques very useful for studying these excitations. Optical properties are also important for the application of semiconductor devices, such as lasers, light-emitting diodes, and photodetectors. If you shine lights on the medium, for example, semiconductors, you will expect some of the light to be reflected from the surface, and some of the light will be transmitted into the medium, and inside the medium, some of the light will be absorbed, or some of the light will be scattered by the lattice vibration. And if the absorbed light can excite the electron from the valence band to the conduction band, and the electron and hole then recombine to give out light, we call that the luminescence. So basically at the surface of the medium, some of the fractions of the incident light is reflected and the rest is transmitted. Photoluminescence is basically absorbing the light, or we call it EM waves, and due to the recombination of the electron and hole, and the emission can be at different frequency, or basically at different photon energy. And also some of the heat can get dissipated as phonon energy. Light scattering by the lattice involved radiation and the scattered radiation. And such a scattered light are usually much weaker. So we can classify scattering into Boolean scattering because these are scattering of lights by the phonon acoustic wave. For Raman scattering, the scattering of lights is by the optical phonons, or sometimes by the plasmon. Plasmons are basically collective oscillation of the free electron gas. In general, the strongest optical processes are the reflection and absorption because they involved the lowest order of interaction between the electromagnetic waves and the elementary excitation inside the medium. Raman scattering and Boolean scattering are considered second order interaction. Reflection and absorption are considered the first order interaction. And Boolean scattering and Raman scattering, the lights are weaker. So they are considered the second order interaction. In these optical processes of semiconductors, we will consider only the reflection and absorption. Next, we will study the absorption coefficient. We describe the radiation or the EM wave especially for the electric field, as a plane wave of angular frequency propagating in the r direction, which is the distance in xyz with a velocity v given as follows. It's easier to deal with the equation in one-dimensional case. So the r, the three-dimensional direction, we will consider only one direction. So that will be the x direction. So instead of vector quantity, it will become a scalar quantity. So k dot r will be just kx, and then minus omega t, where omega is your angular frequency and t is the time. Now, the phase velocity of the electromagnetic wave is given as v equals to omega k. Sometimes we call this the dispersion relation. So basically, you can replace omega, the k, by omega over v. And the phase velocity is also related to the complex refractive index. So v is equal to c over the complex refractive index, where c is the speed of light. And the reflective and the complex refractive index is equals to n plus I Kepler, where n is the real part and Kepler is the imaginary part. And this is known as n is the refractive index and Kepler is the extinct coefficient. If you substitute the complex refractive index by n plus I Kepler into here, then your velocity, you take the inverse of the velocity, you can rewrite in this equation. And then you substitute 1 over v into equation 2.2 for this 1 over v. You can rewrite the radiation as follows. So this is the expression you will obtain, and you can break up into 3 parts. We define the fraction of the incident power or the incident intensity available after propagating a distance x as modular squared of the radiation field at x distance over the modular square of the electric field at x equals to 0. So the modular square is basically the electric field times the complex conjugate. Similarly for the denominator. So for the complex conjugate, basically you change your I, both here, I to minus I. So now minus I will become I. And then you multiply by the same factor, and you will get E minus alpha x, where alpha is 2 omega Kepler over c. Omega is related to frequency, so it's 2 pi mu over c. And you know that the speed of light is equals to frequency times wavelength. So frequency over the speed of light will give you 1 over lambda. So you can see that your absorption coefficient is related to the extinct coefficient, the Kepler, and wavelength. So alpha is called the absorption coefficient and is measured in per cm. So I stress again, this I basically is the intensity of the light, okay, after it propagates a distance x, and is equals to E minus alpha x. Now, by Maxwell equation, you can relate the complex refractive index of a medium to its relative dielectric constant. So I'm not going to go through the derivation, but I will just quote the result. So the relative dielectric constant also have imaginary part, and the real part. And the complex refractive index is equal to the square root of the complex dielectric constant. So you just take the square on both sides, okay, you will get this term, and then you compare epsilon 1 plus I epsilon 2. The real part will be n squared minus kappa squared, and the imaginary part will be 2nk, which is written down here. You can solve numerically, okay, using these two equations to obtain the real part of the complex refractive index and the imaginary part, the kappa, which is the extinct coefficient, as a function of epsilon 1 and epsilon 2. Epsilon 1 and epsilon 2, or the relative dielectric constant, can be measured, okay, experimentally, and then you can calculate n and kappa, or vice versa. Now, if the absorption of the medium is weak, then we take n is much than k. So there's less of attenuation, or because kappa is related to your alpha. Then you can write your refractive index as n equals to epsilon, square root epsilon 1, and kappa is epsilon 2 over 2n. So down here, epsilon 1, if n is much than k, you can drop the kappa squared, and then n equals to square root epsilon 1, which is down here. Down here, your kappa constant is just epsilon 2 over 2n. So the refractive index and the absorption, because your absorption coefficient is related to your kappa, are mainly determined by the real and the imaginary part of the dielectric constant. Now, the reflection coefficient depends both on n and the kappa. And you can find in any textbook, is defined in this way. This formula gives the coefficient of reflection between the medium, which is the semiconductors, and the air or vacuum, and the normal incident. Basically, the light shines 90 degrees to the surface. If the light comes in an angle, so you have to take into account the angular dependence. Figure 2.2.1 show the transmission spectrum of a sapphire. Sapphire are basically aluminum oxide. So this shows the transmission spectra of a sapphire of thickness 3 mm. The bottom panel shows the transmission spectra of a cadmium selenide semiconductor, which is a 2,6 semiconductor of thickness 1.67 mm. So this is a plot of transmission as a function of wavelength in micron. So this region is the UV wavelength. This gray portion, okay, define the visible region, and the rest is basically in the infrared. Now, sapphire itself has a very high transmission in the visible region. Okay, so it's somewhere between 0.2 micron, okay, probably all the way to 3 micron. Okay, slightly even extend to the infrared region. So this part, which is quite flat, okay, define the transmission range, okay, for the sapphire. So this defines the transparency range of the crystal. So basically in the visible region or the visible spectrum, okay, the transparency region explain why the sapphire appear colorless and transparent to the eye. Now, you can see that the spectrum drop quite sharply in the UV region, okay, around here, less than 0.2 micron, down here, less than 0.2 micron. Okay, this is due to the absorption by the bound electron. Okay, the band gap of sapphire, basically, sapphire is an insulator, but of course there is a gap. So the band gap itself is about 8.8 eV or about 0.14 micron. Okay, if you come in with a UV light shorter than 0.14 micron, you can basically excite the electron in the valence band all the way to the conduction band of the sapphire. So we call this the absorption by the bound electron. Now, within the transparency range down here, the transmission is very high, okay, about 80 to 90%. So the absorption coefficient is very small. So less of the light is absorbed. So you can take the refractive index to be real with no imaginary component. And the refractive index in this region is approximately constant, about 1.77 in sapphire. And then there's a dip, okay, in the infrared region, about 3 micron. And then there's a peak, and then it drops very suddenly, okay, in the infrared region. So all these dip and drops, okay, in the transmission is due to the vibrational absorption, basically absorption by the lattice, or sometimes we call that the phonon absorption. Now the cadmium selenide, so the base is a 2,6 semiconductor, so it covers the range of about 0.7 micron to about 11.5 micron. The band gap of cadmium selenide is about 700 nanometer. So it's around here. And then if you convert to energy, it's about 177 eV. So 1, 2, 3, 4, 5, 6, 7. Okay, beyond this line. So this is the band gap of the cadmium selenide. Okay, so there's no visible range transmitted, okay, down here because the transmission dropped. So basically the crystal appear dark, metallic to the eyes. So we have a transparency range, okay, basically most of light is absorbed at the short wavelength or even close to the visible wavelength, and the lattice absorption in the long wavelength. So the maximum transmission is about 60%. Okay. And the rest of the percentage, let's say 40%, are due to the surface reflectivity. Now, next few slides, we want to obtain the transmission coefficient. Okay, how much is being transmitted? So imagine you have a piece of semiconductors, Okay, down here we exaggerate a bit. The thickness from here to here is L. So this is the front surface. This is the back surface. R1 is a reflection coefficient at the front surface, and R2 is a reflection coefficient at the back surface. If you come in with an incident light of intensity I0, some part of the light will be reflected and some part of the light will be transmitted. So the part of the light that is reflected, the incident light or the incident intensity will multiply by a factor of R1. And then those transmitted, you multiply by a factor of 1 minus R1. And we have studied the fraction of light, okay, that propagate through a distant x. It goes like an exponential decay. So it's E minus alpha L. Down here, E minus alpha x or E minus alpha L. That is the distance. So the propagation inside the semiconductor, which is due to the absorption, will be this factor multiplied by E minus alpha L. Okay, and then at this surface, some will get reflected, and then some will get transmitted. Those that get reflected, you take this term multiplied by R2. There's at the back of the surface, so R2. And those that get transmitted, you take this term multiplied by 1 minus R2. So you have 1 minus R2. Again, the light propagate down, and then you have to multiply by a factor of E minus alpha L. So now, instead of E minus alpha L, you will have E minus 2 alpha L. And then at this surface, some of the light will get transmitted. You have to multiply by a factor of 1 minus R1, and some of the light is get reflected. You have to multiply by R1. So multiple internal reflection. So the transmitted light is basically you have to add up all this term. So we have air, medium, air situation. Air, medium, air situation. And it's easier to see if we assume the front and the back reflection coefficient to be the same. R1 equals to R2 equals to R. So the transmitted intensity or the transmitted light, you sum up all this. So that will be this term. And you use some mathematical identity, you convert this formula into this term. So the transmitted intensity, the equation will be I naught, the incoming incident intensity times 1 minus R squared E minus alpha L, another term, 1 over 1 minus R squared E minus 2 alpha L. If you bring the I naught over, it will become IT over I naught. That gives you the transmission coefficient, which is this term. If you assume alpha L is large, that means alpha L is much, much greater than 1. You can approximate this term, the transmission coefficient, to be 1 minus R squared E minus alpha L. So basically, you drop this term. Of course, you also can find the reflection coefficient, okay, for air, medium air situation by summing all these reflected light, okay, the intensity that is get reflected. So If you know the reflection coefficient of a particular medium or semiconductor, and you know the thickness of the sample, then either this equation or this equation, you can solve for absorption coefficient. Now, if R, the reflection, is not known, you can measure the transmission coefficient of the two samples having different thickness L1 and L2. And then you can take the ratio. So T equals to 1 minus R squared E minus alpha L1 divided by T2, 1 minus R squared E minus alpha L2. So the 1 minus R squared cancel off because you are growing the same sample but of different thickness. So that term of R should be the same. So 1 minus R squared term will be cancelled off. And then what you remain is basically the transmitted intensity for thickness L1 and transmitted intensity of thickness L2. The transmitted intensity can be measured. Thickness you know, you can measure, you can obtain the absorption coefficient. One example, a measurement is performed to determine the transmission coefficient at a photon wavelength of 0.89 micron for two gallium arsenide sample S1, S2. The thickness are 250 micron and 350 micron. And you are given the transmission coefficient for two samples, T1 and T2, okay, because that is related to your transmission intensity. Determine the absorption coefficient and the reflection coefficient are at the same wavelength. Of course, we have to mention the same wavelength because the absorption coefficient is dependent on the wavelength. And let's say we assume alpha L is much greater than 1. So you use the equation here. Okay, you take the ratio. So 1 minus R squared will cancel off. And you substitute all the values. And you will get alpha equals to 1.6 times 10 to the power of 2 per cm. So you have to be careful here. The exponential term is a dimensionals. So your L1 is 250 micron to convert to cm. Okay, so then alpha will be in per cm. And you can measure, you can then substitute using one of the equation. T1 equals 1 minus R squared E minus alpha L1. Since you already know alpha and you know the thickness of the first sample, okay, and you know the transmission for T1, you can find R, which is 0.75. So 75% of the light get reflected. Now, next example. For sapphire, the absorption coefficient is very small within the transparency range. So down here, the transmission is very high. So we define this as the transparency range. So the light basically will pass through, so it appears transparent to you. So we take the complex refractive index to be real in this region. Okay, so there's not much of attenuation. So the imaginary part, okay, can be taken as 0. And it left the real part, which is the refractive index, which for sapphire is 1.77. Now we calculate the refractivity and the transmission coefficient for sapphire in this transparency range. So you use this formula, okay? So since the absorption coefficient is very small, within the transparency range, alpha tends to 0. And remember, your alpha is related to extinct coefficient. So alpha is 0, your coupler, the extinct coefficient will be 0. So this is 0, this is 0, n is 1.77. By substituting inside, you will get the reflection coefficient to be 0.077. So 7.7% of the light get reflected. Assuming alpha L is much greater than 1, you can use this formula, okay, using 2.218a by substituting R to be 0.077, and then you can basically obtain the transmission coefficient down here to be 0.85. Okay. We assume the thickness of the sample L for this case to be 3 mm. So L is known. Okay. Alpha is 0 because alpha tends to 0. Or in fact, you do not need to know L because alpha is 0. So this term is 1 and this term is 1. Okay. And R is 0.07, 0.077. Then you can get the transmission to be 0.85, so 85%, which is close. Okay, you can see from the experimental result. Okay, about 85% of the light get transmitted. Now, let us go into further details of the absorption coefficient in semiconductors. As we have just mentioned, the absorption coefficient, okay, is related to the wavelength and therefore is related to the photon energy. So if a light beam is propagating in the x direction, the intensity I, or sometimes we call that the optical power per unit area, which is watt per cm squared, or sometimes we call that the power density, at position x is Ix. So let's say you have an incremental thickness of dx. The decrease of intensity will be dx times I multiplied by a factor of the absorption coefficient. Okay, that's the attenuation. By taking the integral on both sides, you can obtain this equation. This is similar to the equation that we have mentioned in the right at the beginning, where the intensity of the light after propagating a distance x is actually E minus alpha x. So incident power, sometimes we call that the intensity or the power intensity. So I is equal to E minus alpha x. So this is consistent. I equals I naught E minus alpha x. So I naught is the intensity at x equals to 0. And then inside the semiconductor, the medium, the intensity decay exponentially as E minus alpha x. If your sample is too thick, okay, so let's say T, x equals to T, the thickness, and the thickness is very thick, so E to the power E minus, let's say, infinity, then you will not expect any light to be transmitted through the sample. So you can see that the intensity of light in the semiconductor down here is I equals I naught E minus alpha x. Okay, we take the assumption that reflectivity is equals to 0 for our analytical calculation. Otherwise, you can see here I equals to I naught. If you take I0, you have I equals I naught E minus alpha L, or I naught E minus alpha x. Okay, that's just to basically assist us in the calculation, okay, for illustration. Penetration depth is also another term often encountered in semiconductors textbook. The penetration depth is defined as a distance in which the light intensity decay by a factor of 1 over E. So I equals I naught E minus alpha x. So if I is decay by a factor of 1 over E of the incident intensity, so I naught times E to the power minus 1 equals to I naught E minus alpha x. Now I call it the D. So you can basically manipulate the term by cancelling off I naught. You will get D equals 1 over alpha. So specifically, this x we call D is known as the penetration depth, which is inversely proportional to the absorption coefficient. So you can see the light intensity as a function of distance. And these are the penetration depth. Next, another example. If you use germanium as a detector for optical communication to detect the gallium arsenide laser with an emission energy of 1.43 eV, calculate the thickness of the detector that need to absorb 95% of the optical signal entering the detector. So we take the germanium absorption coefficient to be 2.5 times 10 to the power 4 per cm at this photon energy. Remember, absorption coefficient depends on wavelength, and wavelength you can convert to photon energy. And we use this formula I equals I naught E minus alpha x. We assume reflectivity to be 0. So this is a piece of thickness of the sample. This is a front surface, x equals 0, and this x equals to L, so the thickness is L. This is a transmitted intensity. So if I put I become IT equals, it will be equals to I naught E minus alpha, the x will be the L, which is the thickness of the intensity. So I'm measuring the outgoing intensity or the transmitted intensity. Now, here 95% of optical signal entering the detector, which means that 5% will get transmitted. So the ratio of transmitted over incident should be 5%. Okay, since 95% is absorbed. So you can take ln on both sides, and then you basically can calculate the thickness of the sample. Should be about 1.2 micron. Of course, in the formula itself, okay, when you calculate the alpha will turn out to be cm. You have to convert to micron. Another example, this is a schematic diagram of a photodiode detector, and emit of PIN junction. So this is P-type, this is N-type, this is an intrinsic layer. So the photodiode, okay, basically have an active length illuminated by a light beam of optical power P. And the photon energy H bar omega. So there's a missing H bar here. Should be H bar omega, photon energy. The diode is operate in reverse bias and a strong electric field across the eye region. Now, reverse bias because you want to ensure there's only very small current in the circuit when no light is present. So when you shine light, okay, the photon absorbed in the intrinsic region will generate an electron and hole. And then if we apply a bias, reverse bias voltage, so this is positive side, you basically attract the electron, and this is the negative side, you attract the hole. So the electron hole pair are rapidly swept towards the contact by the field because you actually set up an electric field here, okay, by pulling the electron and hole apart due to reverse bias. And then, of course, all these electron and hole contribute to the external circuit. So the diode is operated in reverse bias voltage, and there is a strong electric field, okay, being across the I region, the intrinsic region. Now, assume each photon generate one electron hole pair, and the quantum efficiency is a fraction of this charge carrier that flow into the external circuit. If we have 100% of the charge carrier flow into the external circuit and there's no loss, the quantum efficiency is 100%. Now, provide an expression of the photocurrent. PC means photocurrent, and we call it photocurrent because you are shining lights into the semiconductor, and the current, we call it the photocurrent. The responsivity of the device, calculate the maximum positive responsivity for the photon of wavelength 620 nanometer. List a few criteria on the design of the practical photodiode. Okay, the flux of photon per unit time impinged on the detector is P over H bar omega, meaning that, let's say in 1 second, what's the number of photons that strike onto the detector? And that is defined as P over H bar omega. Remember, your P is optical power. And power is basically work done over time, or work done divided by time, or joules over second. And H bar omega is measured in joules. So in dimension, this is per second. Okay, so therefore it's per unit time. Using this equation again, the fraction of light that get transmitted, so I become IT, okay, over I naught equals to Lx become L, the thickness of the sample. So the fraction of light transmitted will be of this factor. If this is the light that transmitted and assume there is no reflection, then the fraction of light absorbed will be 1 minus this factor. So that gives you this. We define the magnitude of the photocurrent, okay, to be electron charge. This is the efficiency, the quantum efficiency. This defines the number of photon, okay, per unit time that strike onto the detector. Okay, and this part, 1 minus E minus alpha x, is basically the fraction of light, okay, that being absorbed. So that defines the photocurrent. The responsivity of the device is the ratio of the photocurrent to the optical power. So I over P, so this term you divide by P, so the P will cancel off, that gives you this term. And this is measured in ampere per watt. The maximum responsivity for a 620 nanometer, so the wavelength you can convert to energy, which gives you 2 eV. For efficiency equals to 1, because you want the maximum responsivity, then your efficiency must be 100%. And for high absorption coefficient, all the lights that have been absorbed, then this term must be equals to 1. So this term equals to 1, quantum efficiency equals to 1, okay, you left E, electronic charge 1.6 times 10 to the power minus 19. Photon energy is 2 eV. 1 eV is 1.6 times 10 to the power minus 19. So you multiply by 2. That gives you the value of 0.5 ampere per watt. So that is the maximum possible responsivity for photon of wavelength 620 nanometer. Next, list a few criteria on the design of practical photodiode. Now, the design of practical photodiode must depend on the choice of the semiconductor material so that you can optimize the responsivity to ensure fast response and low noise. Okay, especially the noise, okay, it comes from the dark current. And usually this dark current is due to the reverse bias leakage current. And even when there's no photon entering the device, there's always a generation of electron and hole within the depletion region of the device. So these are the leakage current, and this contributes to low noise. Now, first criteria, the band gap is less than the photon energy. So basically, the material itself, the band gap must be less than photon energy so that the incoming photon energy can be absorbed by the semiconductor to excite from the valence band to the conduction band. Okay? Or you can at least overcome the band gap. Otherwise, there will be no absorption by the semiconductors. So the photon energy must, of course, greater than the band gap of the semiconductors. Then we want the band gap to be as large as possible, of course, to be less than the incoming photon energy. And to have large band gap, the reason is because, as I said, we need to minimize the dark current. So with small band gap, it's easy to generate electron hole pair, even there's no photon, okay, because of the temperature. So you have thermal energy, okay, that easily break the bond and generate an electron hole pair. Next, we want a material which electron and hole mobility are high. So you can sweep the carrier across the semiconductor to the contact as fast as possible. In order to have a high electron or hole mobility, you need to have small effective mass for the semiconductor. So you need to look for semiconductor reasonably to have large band gap and also small effective mass, because mobility is Q equals to Q tau over N. So your mobility is inversely proportional to the effective mass, and that will give you high mobility. Of course, material with direct band gap are better than those with indirect band gap, because that will have more efficient in the absorption of the light without involving any phonon energy. The top contact should be mid-thin to transmit as much of the light into the eye region as possible. So this part, the top contact, should be as thin as possible, okay? So that you can have a window, okay? That you can have a photon energy, they're able to impinge onto the sample into the eye region, which is the intrinsic region, okay? So that is the practical design of the photodiode. Now, I think it's important that we discuss a bit on the conversion of the photon energy to wavelength. So for example, what is the wavelength for the photon energy, which is we call h bar omega of 1 eV. Now, h bar omega is angular frequency. So it's 2 pi mu. Mu is a frequency. H bar is basically h over 2 pi. H is the Planck constant. So 2 pi and 2 pi cancel off. Okay, you will have H mu. Now, H mu, the mu itself is frequency. The speed of light is frequency times wavelength. So frequency now is c over lambda, where c is the speed of light. So with this equation, you can convert photon energy in joules or EV to wavelength. Now, 1 EV is 1.6 times 10 to the power minus 19 joules. So for 1 EV, let's say you substitute into this equation. So 1.6 times 10 to the power minus 19. And then your Planck constant is 6.626 times 10 to the power minus 34 joules second. Speed of light 3 times 10 to the power 8 meter per second. The wavelength will give you in meter 1.24 times 10 to the power minus 6. Then that gives you 1.24 micron. So essentially, 1 EV gives you 1.24 micron, okay, for photon energy. If you look at the equation itself, the photon energy is inversely proportional to wavelength because your Planck constant and the speed of light are constant. So h bar omega, the photon energy, is inversely proportional to the wavelength. So you can calculate the wavelength for 300 nanometer by just taking a ratio. Then you have 124 nanometer times 1 EV over 300 nanometer. Since we know that 1 EV is 1.24 micron. So now this is 300 nanometer. I convert my 1.24 to 1240 nanometers to be consistent. That gave me 4.13 EV. What is the wavelength for photon energy of h bar omega equal 1.5 EV? So h bar omega photon energy is inversely proportional to wavelength. Okay, so you can take the ratio by finding the wavelength for 1.5 EV. So wavelength will be 1.24 micron times 1 EV over 1.5 EV. That will give you 0.827 micron. And you can convert to 827 nanometer. So for a semiconductors engineer or engineer working in semiconductor area, they always remember this number, 1.24 micron equals to 1 EV. Okay, so you don't need to go through the step of multiplying the Planck constant and the speed of light, so on and so forth. So as long as you know 1 EV is 1.24 and the photon energy is inversely proportional to the wavelength of light. And then you can calculate for any other photon energy or any other wavelength. Now, we come back to the absorption coefficient, in particularly related to semiconductor. The absorption coefficient depends on the photon energy and also many other factors. Now, I will just give you the expression. Okay, you can find in many textbooks the derivation of this equation. It could be quite tedious. Ni is the density of the electron in the initial state. Nf is the density of available state or the final state. So imagine you come in with a photon energy, you want to excite the electron from the valence band to the conduction band. So your valence band is the initial density of electron in the initial state, which is the number of electron, okay, in the valence band. That is your density of state, okay, per unit volume. And then get excited to the conduction band. In order to go into the conduction band or make a transition of conduction band, you must know what is the available state, okay, in the conduction band, which is your final state. So therefore, that is the density of available state or empty state, which is the conduction band. So it's a product of Mi and Nf. P, K, IF means initial and final. Again, the transition probability from I to F, valence band to the conduction band. And it's important to know this because it's basically what is the probability of the electron making a transition from the initial state to the final state. And then you sum up all the term. And of course, there are also other factors involved. We call that the dynamic as a constant. Okay. So the absorption coefficient, okay, if you take an integral, you substitute the expression for initial intensity, final density, transition probability, which involve a bit of quantum mechanics, you will get this term. So the absorption coefficient is a function of photon energy. Eg is the band gap. Now, Mr is a reduced mass. Okay, reduced mass is 1 over Mr equals to 1 over Me star plus 1 over Mh star, where Me is a electron effective mass, Mh is the hole effective mass. That is the reduced mass. H bar is H over 2 pi. So all these are constant. So I put this as a constant. So you can see the absorption coefficient is basically depends on photon energy, like a square root dependence. This value C, okay, down here, of course, is material dependence, depends on the effective mass of the electron and hole of the material. So usually it's in the range of 10 to the 4. And then absorption coefficient is measured in per cm. So this value H bar and Eg has to be in electron volt. And therefore that will give you per cm. Okay, do not use joules, use EV. And this gives you absorption coefficient in per cm. So the absorption coefficient increases with the square root of the photon energy. We go to square root, that's half. In excess of the energy gap, or called the band gap. Okay, so you can see that if my incoming photon energy is equal to the band gap, so this is Eg minus Eg will be 0. So the absorption coefficient will be 0. This figure shows the plot of absorption H, or the absorption coefficient, as a function of photon energy. So the solid circle here is the experimental result. The dash curve is the theoretical curve. And this curve is plot for the absorption of gallium arsenide. Based on this equation, okay, it goes as square root dependence. So if I plot or fit to this equation for this experimental result, it will go like this. It's a square root dependence. Okay, and this part where H bar omega is equal to the band gap value, the absorption will be 0. So this part should give me the band gap. But more often than not, okay, sometimes you will see the absorption start to occur even below this band gap. You can see there's signal over here, the absorption coefficient, their values. Okay, so this part usually we call that the band tailing. And this could be due to some kind of a disordering in the semiconductors, okay, which we shall discuss later. Now, another experiment Okay, indium arsenide, you measure the absorption coefficient as a function of photon energy. If you take the square on both sides, then you can plot alpha squared as h bar minus Eg, multiply a constant. So you should get a straight line, alpha squared as a function of h bar omega, if you take square on both sides. Again, where the part where alpha squared equals 0, that defines the band gap. So indium arsenide, the band gap down here will be 0.34 eV. And this part is straight. And this part has no signal. Of course, you can also plot the gallium arsenide as alpha squared over photon energy. Okay. But you won't expect that this part to be flat. So you expect that there will be some kind of a tailing effect. Okay, because there's absorption coefficient signal below the band gap. Now, in order to talk about this band tailing effect, or sometimes we call that the exponential band tailing, or we call that the Urbach rule. Now, Urbach basically said that absorption coefficient below the band gap energy can be expressed in this form. So if you look at the next graph, absorption as a function of photon energy, it should go like a square root dependent. So it should go like this for ideal semiconductors, like this, square root dependence. But Urbach rule say that there is actually an exponential tailing effect down here. Okay, and the equation is modified in this form. Okay, with having an exponential term. Okay, so if you plot this equation, you go like this. Let me come like this. Well, for ideal semiconductor, we have derived the band gap should be like this, square root dependence. So for this expression, alpha naught is an experimentally determined absorption coefficient at the band gap energy. So h bar minus Eg, if the photon energy equals to the band gap, alpha equals to alpha naught. Now, the delta E is the characteristic energy, which is known as the Urbach energy. So Urbach energy actually determines how rapidly the absorption coefficient decreases below the band gap energy. So for example, if we were to plot this graph for the Urbach energy or the Urbach band tailing, this equation. And of course, from this curve, you can find delta E. So we call this the Urbach energy. So delta E, you can actually obtain from this equation. You can basically take ln on both sides, and then you differentiate, okay, alpha respect to h bar omega naught, you can find delta E. What is so important about this delta E is because if you have any semiconductor sample and you measure the absorption coefficient, and instead of the ideal absorption semiconductor like goes at square root dependence, and you will plot this curve to find the delta E. So for example, in semiconductor, before annealing and after annealing, the delta E will basically tell you that if after annealing, delta E decreases, it actually improves the quality of the film. So most of the semiconductor, after you grow, you may want to do some heat treatment, okay, basically to treat some of the defect. And you can see that if delta E decreases, therefore, it actually helps, or you have improved the quality of the film. And Hubbard rule actually was not originated to discuss semiconductors. It was actually reported in alkali halides. Okay, alkali halides are like lithium fluoride, sodium fluoride, or potassium chloride, sodium chloride. These are called alkali halides, and they have been observed in many ionic crystals. So they use Hubbard rule to extend also to discuss this kind of exponential band tailing in semiconductor. Especially, you observe a lot of band tailing effect or exponential band tailing in amorphous semiconductor, or especially when semiconductor are heavily doped. Okay, ideally in pure semiconductor, you would expect this kind of absorption coefficient. Okay, goes like a square root dependence. So let us talk more about the band tailing effect again. Okay, so imagine that you have semiconductor that are heavily doped, degenerate, as we mentioned down here, degenerate doped crystalline semiconductor. So then you expect, okay, this is your conduction band. Usually draw two straight line, conduction band, valence band. If the Fermi level will be inside the conduction band, let's say you dope heavily with N-type semiconductor. Okay. Now, it's because that you're doping it so heavily, you have ionized donor near the band edge of the semiconductor. Above it is full of electron, okay, randomly distributed. So let's say you have a lot of electrons over here, and you have ionized donor, you will tend to have a Coulomb attraction. So this ionized donor tend to have an attractive force on the conduction electron. So you tend to have a dip. Similarly, for valence band, you will have a repulsive force because you are going to have an acceptor and a hole. Then the conduction band itself, okay, is not the two straight line that you always draw. So you have a undulating, okay, like undulating effect, okay. And that because the semiconductor was heavily doped and you tend to have a dip, okay, here and there. So in terms of energy band diagram, you plot energy as a density of state, okay. So you expect this curve to be quite parabolic because E equals to H bar squared, K squared over 2M. So E is proportional to K squared, so it's parabolic. Okay, goes the polynomial to a degree 2. But because of this band tailing, okay, the density of state actually tail into the conduction band. Okay, so from here to here is the conduction band, is the band gap. But now your conduction band is tail into the band gap. And also for the valence band, okay, the density of state also tail into the band gap. Okay. So these are the band tailing. So band tailing is actually due to the spatial fluctuation band edges. Remember, when you plot two straight lines, you're plotting energy against x. X is real space. Okay, so it's spatially fluctuating. Okay, when you plot E as a function of density, okay, you're plotting E as a function of K, and K is in the momentum space. So this is a momentum space energy diagram. This is a spatial energy diagram. So the spatial or spatially fluctuating band edge, the band edge is fluctuating, okay, or the band edge is undulating, is because of the random distribution of this kind of impurity. So in terms of energy diagram, okay, instead of very nice, okay, E is proportional to K squared curve, you have this band tailing effect. It tail into the band gap. So at high concentration, some of these are impurity state may form impurity band. Okay. So you can see that the dashed line show the parabolic density of state in ideal condition for undoped semiconductor. But if you dope heavily, you may have this band tailing into the semiconductors. And if you come in with a photon energy, okay, you can absorb, okay, from the top of valence band into this tail state instead of going all the way to the conduction band edge. This is already your conduction band edge. So instead of the absorption start at this band gap, we can start at a lower energy, okay, due to the band edge. This is an absorption curve for some of the direct and indirect semiconductors. Okay, silicon, germanium, indirect semiconductors, gallium phosphide, indirect semiconductors, indium arsenide, direct semiconductors, indium antimonide, direct semiconductors, indium phosphide, direct semiconductors. So it's all listed here. Okay. Now, if we compare gallium arsenide blue curve and the silicon red curve, the transition rate, that's how far the electron make a transition from the valence band to the conduction band. For silicon, the transition rate is smaller. You can see that the absorption coefficient rise, okay, not as fast as compared to the gallium arsenide. It rises quite sharply. Okay, so the transition rate for indirect transition, like silicon, is smaller compared to gallium arsenide, which have a direct absorption. Silicon has a direct band gap of 1.12, and gallium arsenide have band gap of 1.42 eV. Now, the absorption rises much faster in the direct band gap. Okay, and then you exit the indirect band gap. Okay. An example, gallium arsenide is a direct semiconductor with a allowed direct optical transition at the absorption edge of 1.43 eV. Now, this word absorption edge we encounter quite often. In the absorption experiment, down here, this is known as the absorption edge. Okay, this is also the absorption edge. And the absorption edge is associated, sometimes we call the band gap energy. So this is the absorption edge. But if you have band tailing effect, sometimes we call the absorption edge occur in the lower energy. Then this becomes the absorption edge. Ideally, this should be the absorption edge. So the absorption edge, okay, without taking into account the band tailing effect, the absorption edge is actually the band gap energy. So it's 1.43 eV. So the band gap is 1.43 eV. Now, the absorption coefficient is given to you at 1.54 EV photon energy. So it's 2.83 times 10 to the power 3 per cm at this photon energy. 1.43 EV will have its own absorption photon energy, will have its own absorption coefficient. Okay, but I'm only giving you the photon energy, okay, 1.54 EV with an absorption coefficient of this value. Calculate the absorption coefficient at 1.5 EV. Now, absorption coefficient, okay, is equals to this term, let's say square root dependence, without taking the band tailing effect. So the band gap is the absorption H is 1.43 eV. And this is the photon energy. Absorption coefficient is function of photon energy. Now, C is the universal constant. By taking the ratio, you can cancel the C without calculating the C. So you're finding the absorption coefficient of 1.5 eV. So 1.5, you substitute inside alpha, you do not know. You take the ratio for 2.83 times 10 to the power of 3 absorption coefficient at 1.45. So that is 1.45. So you cancel the C, you can find the absorption coefficient, okay, at 1.5 eV. Okay. Remember, all these measured in eV, absorption measured in per cm. Now, given a reflection coefficient of 0.25, what is the transmission coefficient of a 3 micron thick gallium arsenide at 1.45 eV? Okay, now, reflection coefficient 0.25, sample thickness 3 micron, convert to cm. 1.45, what is my absorption coefficient? Is this value. Okay, so if I use the standard formula for the transmission coefficient, you just need to substitute the R value, alpha at 1.45, and the thickness 3 micron. You convert to cm, okay, because your alpha is also per cm, so this term is dimensional. You should get transmission of 0.24. Now, absorption experiment is a very powerful experiment to measure the band gap. Before we talk about the experiment, let us do some analysis. What do we intend to measure? In this experiment, we intend to measure the band gap. So if we go back to this equation in the very beginning of the chapter, this is a transmitted intensity after passing through the sample. This is the incident intensity. This is the reflection coefficient. Alpha is the absorption coefficient, T is the thickness, okay? And then you multiply by this factor. Okay, so this is in the first part of the chapter 2. Now, remember alpha is a function of photon energy, so it's related to h bar omega. But remember h bar omega, okay, is 2 pi over mu, h bar is h over 2 pi, so hc over lambda. So the photon energy is related to the wavelength. And reflection, the reflectivity basically can be measured. Transmitted intensity can be measured. Incident intensity can be measured. Thickness of sample, of course, can be measured. Lambda also can be measured. So these are the measured quantity. Okay. So the only value that you need to find is alpha. So if you can plot, if you have all the rest of the value and you can plot alpha with the incoming photon energy or incoming wavelength of the light, you can obtain the band gap energy. So in this experiment, okay, this is your sample down here. You use a xenon lamp, which is a light source, and the xenon lamp is a wide spectrum of wavelength. It ranges from 0.3 to 3.5 micron. So this is basically the spectrum of the xenon lamp. Okay, in the intensity as a function of the wavelength. So there are certain spikes down here which you should try to avoid, because that will give you the interference in your measurement. So you can measure within this range. Now, you will use a monochromator, okay? And if monochromator have a diffraction grating, so if you turn your grating, if you have light shining on it, you can basically disperse the light and you can select a particular wavelength to be shined onto your sample. So the light source, the xenon lamp, okay, shine into the entrance of the monochromator. Okay, these are mirror, mirror, mirror. So the mirror will get reflected onto the diffraction grating. This diffraction grating basically is mounted onto a turret. It can rotate, and then by rotating, you select a particular wavelength of this incoming photon energy. Okay, and then this is the exit slit. Okay, filters to filter away some of the unnecessary wavelength of the photon energy, and then you can have a nice photon energy of a particular wavelength that shine onto the sample. The sample itself cannot be too thick. It has to be thinned down so that light can be absorbed and also transmitted through the sample. And then you have a photo detector to detect the signal. Okay, and then you go, the signal itself, okay, can convert to current, and this locking amplifier basically to amplify your signal, and then you can connect to the computer. So this part, you measure the transmitted intensity, and then this turret, the reflection grating, you also connect to the computer, where the computer can turn, okay, the diffraction grating to select the wavelength. So you have an input of the transmitted intensity and the wavelength. Okay, and of course, the rest also can be connected to the computer. For example, the incoming intensity of the light can be measured also, and the thickness of the sample you can initially measure, the reflectivity you can initially measure. So by going by this equation, okay, the R, the I naught, the IT, okay, the thickness sample can be measured, and then you can measure the absorption coefficient, okay, for each wavelength, okay, or each incoming photon energy. So down here you have 0.3 to 3.5 micron, and then you have diffraction grating. You can always turn the grating such that you can select one wavelength, let's say 1 micron. So this 1 micron, okay, or convert the photon energy, 1.24 divided by 1 micron, you have 1.24 EV of the wavelength of the energy that shine onto the sample. And then you can get one value of absorption coefficient, okay, by plotting alpha against h bar omega. So one photon, one wavelength correspond to one value of the absorption coefficient, because the absorption coefficient is related to this equation. Okay, and remember your absorption coefficient also related in this way. So IT, I naught, R, thickness, all can be measured. Okay, with this, we'll end the first part of the optical processes in semiconductor. The next session will be on the direct transition and also indirect transition of semiconductor with direct band gap and indirect band gap.